Here's how the finished product works in practice. Imagine a growth marketer types. Track changes to competitor X's pricing page and alert me with context if they've added new tiers or adjusted terms. The system springs into action. Browser use automates a headless browser to scrape the pricing page structure, comparing it against historical snapshots stored in Google Cloud. Deep Research spins up a multi-agent workflow. One agent analyzes HTML DOM changes, another cross-references pricing tables with archived data, while a third pulls review sentiment from app stores using LangChain to parse unstructured text. When a new enterprise tier appears, the system synthesizes evidence screenshots of the updated page, highlighted DOM differences, and a summary of user reactions and routes it to the user as a prioritized alert. The output isn't just a change-detected notification. It's a contextual report with visual proof, timeline analysis, and inferred strategic implications. The input boundary is simple: natural language queries about product, pricing, or review changes. The output is always a verified alert package, structured data, evidence artifacts, and an executive summary. Inside the architecture, browser use handles web automation at scale, acting as the eyes of the system. Deep Research coordinates complex workflows, splitting tasks across agents, one for data extraction, another for analysis, a third for cross-referencing with external datasets. LangChain binds this all to LLMs, enabling agents to reason about unstructured content like review text or pricing descriptions. Google Cloud Node.js manages data pipelines, storing historical records, handling authentication for protected pages, and ensuring compliance with scraping policies. Infographic renders the final output into digestible visuals, timelines of changes, sentiment charts, side-by-side pricing comparisons, turning raw data into a decision-making tool. Each repository plays a non-negotiable role. Browser use isn't just automation, it's the foundational layer for reliable, programmatic web interaction. Without it, the system couldn't reliably monitor live pages or handle JavaScript-heavy SPAs. Deep Research adds the rigor of multi-agent validation, ensuring alerts aren't triggered by false positives like temporary price tests. LangChain provides the semantic understanding to move beyond basic scraping, interpreting contexts like discounted annual billing versus month-to-month rate. Google Cloud Node.js ensures scalability and auditability, critical when monitoring hundreds of competitors. Infographic transforms data into actionable insights, recognizing that growth teams need visuals to quickly grasp shifts in the market landscape. Together, they form a chain of evidence, from raw web content to verified, contextualized intelligence. This isn't a theoretical pipeline, it's battle-tested. When a user asks about a competitor's review strategy, the system pulls recent App Store reviews, uses LangChain to cluster themes, bug fixes, UI complaints, cross-references with historical sentiment trends, and flags anomalies like a sudden surge in negative reviews about a new feature. The alert includes a PDF report with quotes, sentiment graphs, and a comparison to the competitor's previous review velocity. All of this happens without the user needing to understand the underlying tools. They get evidence. The architecture handles the complexity. The REST API endpoint accepts JSON payloads with a webhook interface for real-time event notifications. As a competitive market intelligence agent, our product relies on a seamless data flow to provide evidence-backed alerts to product and growth teams. Let's trace a request through the complete system, from the initial browser interaction to the final alert notification. When a user submits a request to track a specific product, the browser use repository takes the lead, utilizing its Python library to automate web interactions and extract relevant data from the product's web page. This data is then passed to the Deep Research repository, which leverages its multi-agent framework to analyze the data, identify trends, and generate insights. The Deep Research repository, built on Spring AI Alibaba Graph, adopts a collaborative pattern, enabling dynamic task planning and execution. It integrates multi-source online search and hybrid RAG technology to acquire comprehensive information. The system then reflects on its output, optimizing the quality of the research report through self-evolution memory and human-in-the-loop feedback. The resulting report is stored in a structured format, ready for further processing. The Google Cloud Node repository enters the picture, providing a backend data storage solution using Google Cloud Platform services. The system utilizes the Cloud Storage API to store the research report, and the Cloud Pub sub-API to publish events that trigger further processing. The published event is received by the LangChain repository, which applies its framework for building agents and LLM-powered applications. LangChain chains together interoperable components, including the research report, to generate a cohesive alert notification. The alert notification is then passed to the Infographic repository, which generates a visually engaging infographic using its declarative infographic syntax. The infographic is rendered as an SVG, ensuring high-quality visuals and easy editing. The final infographic is stored in the cloud storage, and the Cloud Pub sub-API publishes an event to notify the product and growth teams of the new alert. Throughout this process, each repository hands work to the next, forming a cohesive pipeline that transforms raw data into actionable insights, demonstrating the power of a well-designed architecture. Start by scaffolding the core data pipeline. First, wire up browser use to monitor target domains. Define a set of seed URLs for products and review pages, then use its Python library to automate periodic snapshots. Keep it simple. CSS selectors for price elements, review sections, and version numbers. Store raw HTML and metadata in a Google Cloud Node Firestore collection with timestamped entries. Next, integrate LangChain to process these snapshots. Create a base agent using the LLM of choice Claude or Gemini work, well here tasked with comparing current vs previous versions. Use structured outputs to flag changes, price deltas over 5%, new review clusters, or feature updates. Wrap this logic in a daily cron job via Cloud Scheduler, triggering a GCP Cloud function that orchestrates browser automation and analysis. Now layer in deep research for escalation paths. When the LangChain agent detects significant changes, spin up a multi-agent workflow. One agent cross-references competitor pricing from cached data. Another analyzes sentiment in new reviews using Spring AI's built-in NLP tools. A third checks if the change aligns with historical product cycles. Output a prioritized alert score. For local development, use Docker Compose to mimic GCP services. Run a local Firestore emulator, disable real browser automation in dev mode, use cached responses instead, and mock LLM calls with predefined scenarios. Write unit tests for change detection logic and end-to-end tests that simulate a full monitoring cycle against a test domain. Background jobs need careful isolation. Use cloud tasks to queue resource-intensive work, like full site crawls or image processing for visual changes. Rate limit requests to avoid overwhelming target sites, and implement retree logic with exponential backoff in browser use. For production deployment, containerize the agent stack with GCP Artifact Registry, deploy to Cloud Run with autoscaling, and set up logging dashboards in cloud monitoring to track alert accuracy and system health. Finally, connect Infographic for stakeholder reports. When alerts trigger, generate a visual summary showing change timelines, competitive benchmarks, and sentiment trends. Use their declarative syntax to template the TV's SVG. Output works well for embedding in Slack or email alerts. Host static files on cloud storage with signed URLs for secure access. Test the MVP end-to-end weekly. Inject synthetic changes into a test site, verify alerts fire correctly, and audit the generated infographics. Iterate based on false positives negatives, refining selectors and thresholds. Keep the first version focused on a single e-commerce category to validate the feedback loop before scaling. Browser use starts by setting up a Python environment with version 3.11 or higher. Install via pip using pip install browser use, then add your LLM API key to a env file. For self-hosting, developers can run the service locally or deploy through Browser Use Cloud, though the latter requires a paid plan for high-volume usage. Deep Research demands Docker for its secure sandbox environment. Run Docker Compose up after configuring API keys for search services like Tavily or Aliyun. Google Cloud Node, its clients are installed per service via NPM, with authentication handled through Google's default credentials chain, typically set via Google Application Credentials environment variables. LangChain requires LLM provider keys in environment variables too, like OpenAI API KE. and supports both Python and JS setups. Infographic needs global installation via npm with npm install g at antiv Infographic, then generates visuals through CLI commands or embedded in web apps via their React component. The system's limitations are clear. Browser use benchmarks show occasional failures in complex multi-step tasks, and deep research's multi-agent coordination can become computationally heavy with unbounded task scopes. Google Cloud Node.js clients tie you to their ecosystem costs, while LangChain's flexibility demands careful tool selection to avoid over-engineering. Infographic's AI-friendly syntax works best with structured prompts. Freeform text might not map cleanly to its template system. To start, a developer could run pip install browser use and Docker compose up for deep research, then test a synchronized agent workflow. How would you handle rate limits when combining Google Cloud's search APIs with multiple LLM calls in the same pipeline?